Okay, let's unpack this. Imagine a concept so fundamental, maybe even a bit abstract sounding. It was born, way back in theoretical physics. Think Einstein, space-time, that kind of thing. You might have heard the name, maybe whispered in a tough university class, felt a bit
Yeah.
intimidating. But now it's having this massive moment. Suddenly, it's just everywhere in tech talk. Almost every conversation about modern AI, you hear it. We're talking about the tensor.
Yeah, it really is quite the turn, isn't it? This thing that felt so esoteric, a real workhorse tool from the deepest parts of physics. And somehow, quietly but definitely, it's become the foundational language, the DNA almost of the AI revolution.
Right. So our mission today, here on the Deep Dive, is to really get into that incredible journey. It feels almost improbable. How did this idea, first thought up to describe the unchanging laws of the universe, physical reality, how did that become the absolute engine building our artificial realities?
It's a fascinating question.
We're going to be diving deep, looking at insights from William L. Weaver's piece, from Relativity to the AI revolution. It just lays out this whole evolution so well.
It really does. It connects the dots beautifully.
And importantly for you listening, this isn't going to be a math lecture. No dense equations, promise.
Yeah.
Instead, we want to explore the core ideas, the patterns, and just the surprising ways knowledge travels, gets repurposed and then suddenly explodes in a totally different field.
Yeah, it's about how something designed for the fabric of reality itself ended up helping build artificial reality.
Exactly. And what does that tell us about truth and perspective and, well, innovation itself?
It's a great story. And what's really key here, starting with the physics side, is what the tensor was originally for. It's always been about understanding what is, what's fundamental, what stays the same no matter how you look.
Right. The core truth of something.
Precisely. So to a physicist, a tensor isn't just, numbers on a page. It's this profound mathematical object. It's specifically designed to describe some physical property in a way that stays completely independent of your coordinate system, your viewpoint, basically.
Okay, so independent of how you're measuring it or looking at it.
Exactly. Let me try an analogy. Imagine you're measuring the temperature in a room. Say it's 20 degrees Celsius, nice and comfy.
Okay.
That temperature, that physical fact, it doesn't actually change if you decide to call it 68 Fahrenheit, right?
No, same warmth.
Or if you rotate your thermometer or hold it upside down, the actual warmth is invariant. It stays the same.
Got it.
Or think about water flowing in a river.
Yeah.
The current has a certain speed and direction. That reality doesn't change if you decide to measure it based on north-south versus, say, along the riverbank.
The numbers might change.
The numbers describing it will change, yeah. But the actual flow, the velocity, it's the same physical thing. The tensor at its heart is the language for describing that.
Yeah.
These inherent unchanging realities without our observational biases messing things up.
Okay, so it's like trying to strip away our own perspective, our human way of measuring, to get at something deeper, more fundamental about what we're seeing.
You've got it. It's like trying to explain something really important, but the other person keeps changing how they listen, and the meaning gets twisted. The tensor is like making that concept so fundamentally clear, so well-defined, that no shift in perspective can actually distort its core meaning.
And Weaver's article really highlights how physicists built this up, right, from
Yeah.
simpler ideas. The simplest one being the scalar. That's a rank 0 tensor.
That's right, yeah. Physicists use rank to talk about complexity, kind of. You can think of it intuitively as how many directions or indices you need to pin down the data, dimensionality.
Okay.
So a scalar is rank 0. It's just a single number. It has magnitude, but no direction.
Like mass, or that temperature we mentioned.
Exactly. 5 kilograms of mass. That's just a number. It doesn't point anywhere.
Right.
And a kilogram is a kilogram whether you measure it here or on the moon or upside down. Its value doesn't change based on orientation.
It's invariant.
That's the key word, invariant. The underlying physical thing doesn't change no matter how you look or what units you use. It's like the taste of a strawberry. You could describe it in different languages, but the actual flavor, it's the same.
Right. Okay, so that's the base level. Then we add a bit more complexity with the vector, rank 1.
Rank 1. Now we have magnitude and direction.
Like a force pushing something. Or velocity, like the river current or a car moving.
Perfect examples. If you push something, there's a strength of the push and it's going in a specific direction.
And the key point here for physicists is how it behaves when you change your viewpoint, your coordinate system.
Exactly. This is crucial. If you rotate your frame of reference, say you were describing things based on north-south, but now you tilt your axis, The individual numbers you use to describe that vector, its components along those axes, will change.
Okay, the numbers change.
Yes, the components change.
Yeah.
But here's the genius bit. They change in a very specific, predictable, mathematical way. There's a strict transformation rule. And this rule is what guarantees that the actual thing, the vector represents the force, the velocity remains absolutely consistent.
Yeah. So the description changes, but the underlying reality doesn't.
Precisely. Think of a baseball flying through the air.
Mm.
You could describe its speed going north and its speed going east. But if you suddenly look from, I don't know, a moving train, your coordinate system changes. The numbers you'd use for north and east speed would look different from the train.
Right. Relative motion.
Yeah, but the ball itself is still flying on the exact same physical path through the air. The vector, as a rank 1 tensor with its transformation rule, gives you the math to prove the actual flight path hasn't changed, even though your description number's dead.
That's clever. Without that rule, your physics would be all over the place, depending on how you looked.
It would be chaos. You'd constantly be battling this shifting, unreliable view of reality in your measurements.
Which brings us to the full tensor, rank 2 or even higher.
Yep. This just generalizes the idea. Scalars, vectors, they're just the simpler tensors. Higher rank tensors let us describe more complex stuff, like stress inside a beam or how space-time itself curves in general relativity.
Wow.
And to a physicist, this is the tensor's soul, you could say. It's an entity that captures a physical property in a way that is truly fundamentally invariant. Meaning no matter how you look, what coordinate system you use, what units you measure in, the fundamental reality it describes stays the same, rock solid.
So the tensor lets you hold on to that core truth, even when the problem gets super complex or your perspective shifts.
That's the essence of it. It's about finding and describing the bedrock, verifiable reality underneath the surface description.
Okay, if we connect this back to Weaver's point, this idea of bedrock, verifiable reality is central.
Absolutely central. The tensor gives you that anchor. It lets you hold on to that unchanging foundational truth of whatever you're studying, even as your viewpoint or your measurement system shifts around.
Whether you're Einstein thinking about gravity warping space-time,
Or an engineer calculating stress on a bridge support.
the tensor makes sure the underlying physics doesn't just warp because you tilted your head.
Exactly. It preserves that bedrock truth, which naturally leads to a really interesting question.
Yeah.
How does this incredibly abstract idea, this language for unchanging physical truth, how on earth did it jump over into the digital world? Into AI, it seems like such a different place.
Right. This is where it gets, I think, really interesting. We're shifting scenes completely now from, quiet physics labs thinking about the cosmos to the absolute buzz and explosion of artificial intelligence, the digital universe. And the tensor isn't just some dusty academic thing anymore. It's having this huge cultural moment. Like you said, it's foundational in AI.
It really is.
Okay.
But the key thing is the shift in perspective on what a tensor is.
How so?
In AI, it's primarily understood less as this deep philosophical thing about physical laws and more as a super practical, powerful tool, basically a multidimensional array.
An array. Like a spreadsheet grid, but potentially with more dimensions.
Exactly. It's a generalized data structure, a really organized container for numbers, perfectly designed to hold and manipulate the massive amounts of data AI needs.
So less about inherent physical truth, more about organizing digital information.
Pretty much. The AI world adopted it for its incredible utility and flexibility in handling all the different kinds of data AI learns from.
Okay, let's break that down. How does this array idea work for different data types?
Right. So you can represent almost anything. Start simple. A 0D tensor. Just like the scalar in physics, it's rank 0. It's just a single data point, one number.
Like someone's age, 35.
Perfect. Just one value. No direction, no structure beyond itself.
Okay. Then a 1D tensor, that's like a vector in AI terms.
Yep. Basically a list or a sequence of numbers, an array with one dimension.
So not just one age, but maybe a list of features for one person, like age, height, weight.
Or, like you mentioned earlier, a student's grades.
Right.
90, 85, 92, a single row from a data table. Ordered numbers in a line.
Makes sense.
Right.
And then 2D tensor, that's a matrix, right? Like a spreadsheet grid.
Exactly. And this is commonly how AI represents a grayscale image.
How does that work?
Well, an image is made of pixels, right? Each pixel on a grayscale image has an intensity value, how bright it is, from black to white. So you can represent the whole image as a grid, a 2D array, where each number in the grid is the intensity of the pixel at that specific row and column.
Ah, okay. A table of brightness values.
Precisely. And this matrix structure is super useful because a lot of image processing, like blurring or finding edges, involves sliding smaller grids, little 2D tensors called filters or kernels, across this main image grid.
Okay, I see. And for a color image, that needs more info than just brightness.
Right, so for color, we typically use a 3D tensor. Think of it like stacking 3 of those grayscale grids on top of each other.
3 layers. Why 3?
Usually one layer for red light intensity, one for green, and one for blue at each pixel location. RGB color.
Ah, RGB. Got it.
So a color image tensor often has dimensions like height, width, channel, where channel is those 3 color layers. It's literally a queue of numbers.
And that structure is important for things like convolutional neural networks, CNNs.
Absolutely essential.
Yeah.
CNNs work by sliding filters, which are also often 3D, across these image cubes to detect patterns, like edges or textures, using that spatial and color information.
Okay, this is starting to paint a picture of how data gets structured. What about even more dimensions, like 4D?
Good question. A 4D tensor comes up a lot in training AI models. See, models usually don't learn from just one image at a time. That's inefficient. They learn from batches of images.
Batches, like processing a whole stack at once.
Exactly, for speed and to use hardware like GPUs efficiently. So a 4D tensor might structure data like batch size, height, width, channel.
So the first dimension tells you which image in the batch you're looking at.
Precisely. You've got a whole stack of those 3D color image tensors processed together. It's crucial for making deep learning training practical.
Wow, okay. Can we go even higher? 5D?
You bet. Think of video data. What is video?
It's a sequence of images, right? Frames changing over time.
Exactly. So a 5D tensor can represent video. You add a time dimension. The structure might look like batch size, frames, height, width, channel.
So you've got batches of videos, each with multiple frames, each frame being a color image.
You got it. This lets AI systems process motion and temporal patterns. Think action recognition in videos or predicting what happens next. It's a really neat way to bundle all that complex, time-varying information together.
That's incredibly elegant, actually, the way it just scales up.
It is. And the real genius here, the reason this tensor as array idea took over AI, is its universality.
Universality.
Yeah. Whether it's a single number, a list, an image, batches of images, video streams, seemingly totally different kinds of data, they can all be encoded consistently into these tensors, these numerical arrays.
So everything speaks the same data language.
Exactly. This allows for one single consistent programming model, one set of mathematical operations to handle all this diverse information.
That must have been revolutionary.
It absolutely was. It turned the tensor from this specialized physics tool into the indispensable foundation of the whole modern AI boom.
And it connects back to that bedrock reality idea too, doesn't it?
In a way, yes. Just like physics uses tensors to keep the description of reality stable across different views, AI uses them to represent all sorts of data consistently. It ensures the raw information keeps its structure, its own kind of data reality, no matter where it came from or how it's fed into the system.
Without that, the AI would be trying to learn on constantly shifting sands.
Totally. It needs that stable, reliable representation to build complex understanding upon.
Okay, so this conceptual leap tensor as universal data structure was huge. It set the stage. But then, how did this become practical? How did we actually scale this up to handle the absolutely massive data sets AI uses? Moving from the idea to actually making it work efficiently.
Right. That's where the infrastructure comes in, both software and hardware. And Google played a massive role here. First, the software, TensorFlow. Google released it as open source back in 2015.
TensorFlow, the name is pretty literal then. Tensors flowing.
Exactly. It provides a framework for defining and running computations as graphs. Think of it like a diagram, where the nodes are mathematical operations, addition, multiplication, more complex stuff, and the edges, the connections between nodes, are the tensors themselves. The data flows along these edges, through the operations.
Like a data plumbing system.
That's a great way to put it. And what made TensorFlow and similar frameworks like PyTorch so powerful for AI was something called automatic differentiation, or AutoDiff.
AutoDiff. What's that?
It's the magic behind how neural networks learn. When you build your model as one of these computational graphs, TensorFlow can automatically figure out how changes in any part of the graph affect the final output. Specifically, it calculates the gradients.
Gradients. That's the direction of steepest change, right? Like slope in calculus.
Precisely. It tells the network how to adjust its internal parameters, its weights, to get closer to the right answer, to minimize error.
So it automates the really hard calculus part of learning.
Exactly. It's the engine of deep learning optimization. It lets researchers build and train incredibly complex models without having to manually derive all those derivatives, which would be basically impossible for modern networks.
Okay, that makes the software side much clearer. TensorFlow provides the smart plumbing and the learning engine.
Hmm.
But you mentioned hardware too. Even with clever software, these models got huge, right? Billions, now trillions of parameters.
Insanely huge. And the sheer amount of computation, especially those matrix multiplications we talked about, just started overwhelming traditional hardware.
Even powerful CPUs and GPUs. I thought GPUs were good at parallel stuff.
GPUs are great, much better than CPUs for this, and they drove the initial deep learning boom. But they're still general-purpose parallel processors, designed for graphics and a range of tasks. As models scaled up, the specific needs of deep learning, primarily massive matrix math, became a bottleneck, even for GPUs. The computational hunger was just immense.
So the existing tools weren't quite right for this very specific, very demanding job.
Exactly. It was like trying to dig the Panama Canal with regular shovels. You need specialized equipment. So the solution was build the tool for the job. And that led Google to create the Tensor Processing Unit, the TPU.
TPU. Okay, so how is that different from a CPU or GPU?
Fundamentally different. A TPU isn't a general-purpose processor. It's what's called an ASIC,
Yeah.
application-specific integrated circuit. It's a chip custom designed for one particular application, or a very narrow range of them,
And in this case, that application is?
accelerating the core mathematical operations of machine learning, especially tensor operations.
So it's not trying to run your web browser or your operating system.
Nope. It does one thing, but it does it incredibly fast and efficiently. Tensor math.
It's a specialist, a hyper-optimized engine just for AI calculations.
Exactly. At its core, a TPU is an engine built for linear algebra. It's massively optimized for those huge matrix multiplications and additions that dominate deep learning training and inference.
How does it achieve that optimization?
Several ways. One key feature often found in TPUs is something called a systolic array. Imagine a grid of tiny processing units, all interconnected. Data flows through this grid like waves, getting processed at each step in a highly synchronized pipeline way.
Sounds complex, but efficient for specific flows of data.
Extremely efficient for the kind of dense matrix operations AI relies on. It allows for massive parallelism and data reuse right on the chip. TPUs also often use lower precision numbers like 16-bit or even 8-bit math instead of the standard 32-bit or 64-bit used in CPUs.
Does that hurt accuracy?
For many machine learning tasks, it turns out you don't need that super high precision. You can get away with lower precision, which is much faster and uses way less power and silicon area. It's a trade-off that works really well for deep learning.
So custom architecture like systolic arrays plus lower precision math.
Equals an engine purpose-built for tensor crunching at incredible scale and efficiency. Google designing hardware specifically for the kind of math TensorFlow was doing allowed them and others using TPUs to train and run those enormous AI models, large language models, advanced vision systems at speeds that were just unthinkable before.
That really highlights the connection, doesn't it? The conceptual shift to tensors as data structures in AI software.
Directly drove the need for and the invention of completely new specialized hardware. It's a perfect feedback loop.
This whole story, from Einstein's relativity to these TPU chips crunching AI models, it really feels like the perfect example of what Weaver calls innovation, doesn't it?
Absolutely. He makes that distinction, right, between invention and innovation.
Yeah, he says invention is often like incremental progress within a field, a new gadget, a slightly better process. But innovation, true innovation, is often about taking something established, a workhorse tool from one area.
And applying it brilliantly to revolutionize a completely different area.
And the tensor is just the poster child for that.
Completely. It wasn't about inventing a new math concept. Tensors were already there, solid, understood in physics for, what, over a century?
Yeah, long time.
The innovation was seeing its potential in a totally new context, data representation for AI, reinventing its application, not its core. It's like that shovel analogy you used. Designed for gardening, but turns out it's perfect for digging skyscraper foundations. Same basic tool, utterly transformed impact.
You really do see that pattern elsewhere when you look, like Weaver suggests.
Oh, yeah. Think about signal processing from radar, developed for detecting planes and ships.
Then finds a completely new life in medical imaging, right? MRI, CT scans.
Exactly, seeing inside the body. Or statistical methods from agriculture, meant to figure out best crop yields.
Get adapted and become fundamental to modern finance for risk modeling and stuff.
In every case, it's a powerful, established tool from one domain, recognized for its core strength, and then boom, revolutionizes another field. The tensor's journey is just maybe the biggest, most dramatic example happening right now.
And what strikes me as profound, connecting back to the start, is how its two main uses seem to echo each other, describing physical reality, the invariant laws of the universe.
And representing digital reality, structuring data consistently for AI.
There's this common thread of maintaining truth or consistency.
I think that's a great way to put it. That idea of the tensor providing kind of invariant identity, a stable foundation, it has really big implications for AI's future.
How so?
Well, think about the digital world. Information can be messy, noisy, incomplete.
Or even deliberately manipulated, deepfakes, misinformation.
Exactly. In that kind of fluid, potentially unreliable environment, the tensor, as this consistent mathematical structure for data, can act as an anchor, a mathematical bedrock.
Meaning it helps ensure the AI's internal understanding isn't totally thrown off by noisy or bad input.
It provides a stable framework, yeah. It ensures the fundamental representation of the information inside the system has integrity, consistency. It's not warped just because the input data shifts a bit or has errors. It gives the AI a reliable ground truth for its data upon which it can build its learning.
So, okay, the tensor of Einstein, dealing with space-time curvature.
And the tensor of AI, structuring pixels in an image or words in a sentence.
They might seem worlds apart, used with different accents, as we've put so.
But they share this deep grammar, a language for capturing something essential, something that persists, regardless of viewpoint or format. A language for a kind of truth.
That's a powerful thought, especially now in our age of just information chaos sometimes. Understanding that these foundational concepts like the tensor provide stability and anchor for reality, whether physical or digital, that feels really important.
It's like the silent guardian of consistency, maybe.
Yeah.
In this increasingly complex digital landscape.
Yeah. And it really makes you think, doesn't it, about where the next big breakthrough might come from.
Exactly. It might not be something brand new. It could be hiding in plain sight right now, maybe in an old textbook, some concept from a field we think is unrelated, just waiting for someone to see it
Or
differently.
recontextualized, reimagined.
That power of cross-disciplinary thinking, of seeing connections others miss, the tensor story is just a massive testament to
It
them.
really is. True innovation isn't always invention. Sometimes it's brilliant repurposing.
Yeah.
Okay, so just to kind of wrap up this deep dive, we've traced this amazing path of the tensor from this pretty esoteric physics tool for understanding the unchanging bedrock reality of the universe.
To becoming the absolute fundamental building block of the AI revolution.
Yeah.
Handling data, enabling learning.
It's just a stunning example of innovation taking that mature concept and transforming a totally new field.
And in both worlds, physics and AI, it serves this crucial role as an anchor for verifiable reality, for consistency, for truth, however you define it in that context.
Yeah, connecting it to the bigger picture, it's that powerful reminder. The most game-changing ideas, they aren't always new inventions. Often they're brilliant ways to reuse what we already know.
So maybe something for you listening to think about as you go about your day. What other workhorse tools are out there? Sitting in biology, maybe?
Oh.
Or linguistics, ancient history, just waiting for someone to see them in a new light to innovate them into the next big thing.
Yeah, and maybe also, how can understanding these fundamental sort of invariant truths or stable concepts, how can that help us navigate, whether it's the complexities of physics or AI or just our daily lives in this messy world?
That search for what remains constant, what's reliable,
Yeah.
it could be a really powerful guide,
Absolutely. Well, we hope this deep dive gave you some new insights, maybe spark some connections. It really shows how interconnected knowledge is, doesn't it?
It certainly does.
Thank you for diving deep with us.